Okay, 1, 2, 3. Oh, hi. Didn't see you there. You guys must be here for the physics. Well, let's see, what were we supposed to do today? That's right, we're going to talk about Newton's 3 laws of motion. So, most of you have probably heard of Newton, Isaac Newton, and his 3 laws of motion that help define pretty much everything to do with motion. He came up with 3 laws, and for those of you who don't know, we've got the first law is objects will stay in motion until something acts on them. So, let's say we have a box, and we push on the box, and there's nothing else stopping it. It's just sitting there. And we start pushing it, and there's no forces pushing back on it. If there's nothing pushing it, there's nothing else pushing on it, after it starts going, the first law says that it will keep going until something else stops it. If something else isn't there to stop it, it will go on forever and ever and ever and ever. Now, the second law, it says that the force of an object that you push or pull or whatever stops it from moving is equal to the mass times the acceleration of it. Now, to help kind of define that a little better, mass is how much of something is in an object. So, like let's say a bouncy ball here. This bouncy ball has a mass because based off of how much stuff is inside of this, or maybe us. We have a certain amount of stuff inside of us that makes up our mass. Our mass cannot change unless, let's say, I lopped off an arm. Then, obviously, we're going to have less mass here. But there's also weight to take into consideration, and weight is different from mass in that the Earth has gravity. It pulls down. So you're going to be pulled down to the Earth, which is the force, or how fast you're moving with the acceleration times your mass. So how much stuff you have in you, the mass, times how much acceleration. It's speeding up. So let's say you're being pulled down to the Earth. Right now you're being held on it. The gravity of the Earth is about roughly 10 meters per second squared. So you're being pulled down to the Earth at 10 meters per second squared. So you're being held down onto the Earth. But your mass times that acceleration gets you your force or your weight. So how much you weigh. So let's say I was shipped off to Mars. Mars has a much smaller density. It doesn't have as much mass, it's smaller. So the amount of gravity that you feel on that planet is going to be a lot less. So your acceleration is less, but your mass doesn't change. So the mass times the acceleration on, let's say, on Mars is going to be much, much less. So you're going to, in turn, weigh less. Now, the third law, that's what we're going to be testing out here today, states that every action has an equal and opposite reaction. So let's say I take this bouncy ball and I hit it against the wall. See? So I push it forward and the bouncy ball hits the wall and pushes on the wall. Now, Newton's third law says that there's an equal reaction. So it goes in and then the wall will push back with the same amount of force that allows it to come off. See? And it just bounces right back. The third law has that equal push with the opposite reaction that is the same amount. So, to help demonstrate this today, let's see, we got a can here. Now, pretty simple. And we've got some holes here. And you can see we've got a few holes. We got a piece of paper on here to help show when it's moving around here. And so we have the holes in here at an angle. So, what we're going to try and accomplish today is to try and show Newton's third law. So let's try and do that here. We've got some water, and we're going to pour our water in here. We're going to try and make sure this guy isn't spinning. Come on now. Okay, and we're going to pour some water in here. Put some water going, and you can see right there. Got the water pushing out, falls down, and the can is spinning. I'll try that again. See, it spins around and around and around. And then it eventually turns back around. There. And it'll keep spinning around and around. There it goes. Now you might be asking yourself, that's a pretty cool sprinkler, but how does it work? It's not magic, is it? Well, no, magic isn't real here. But what is happening is we've got the can, and we've got forces here. So we pour the water in, and the acceleration of gravity on Earth is roughly 10 meters per second. So that water is trying to get pulled down to the Earth. It's trying to get closest to the center as possible. And obviously we got some room here. So it's being pushed down in the can and being forced out these holes. So it's being forced out of the sides here. So it pushes outward, and the more force you're going to have in there, the farther the water is going to shoot out there, because the quicker it's trying to get to the ground with the more force pushing on it. So what makes our can turn here is the fact that Newton's third law, opposite and equal reactions. So the water is pushed out, and as the water is pushed out, forces are trying to push it back in. We have, air pushing onto the can, the atmospheres, how much air pressure is trying to push that water back into the can. But because the water is leaving quick enough out of the can, all you can see from that is the water drooping down, and you can kind of see it arc downward as it goes. That's the air trying to push the water back in, but it can't catch it quick enough. So what happens in turn is the air pressure and the forces against it push on the can, the side of the can, and push against the direction of the water, which allows it to spin. So you can see how it spins, and then it'll eventually, you have the rope all tangled up here, string, then it starts to unwind itself. So it'll keep spinning even after all the water's gone. Well, you're thinking, well, there's no water being pushed out, so how are there forces continuing to push that can? Well, the fact is, there's not. There's something called inertia, which is something's ability to cause something to happen. So let's say I push a box on ice. Say, just ice. You push it, what's it going to do? It's going to keep going. Because the frictional force on it that's pushing back, trying to stop that box, trying to get it to stop moving, is slowing that box down. But at the same time, it's so little compared to the push that it's not going to be able to stop it quick enough for it to just stop on its own as soon as I stop pushing. So after all the water has poured itself out and it's not spinning anymore in the can, there's still that inertia left over, built up from the string and the forces, that it's gonna equally react and spin back in order to run. It's that inertia, the ability to spin. It's spinning and spinning and spinning, and it'll keep spinning back and forth and back and forth, and go back around, until eventually the air resistance stops it all the way, brings that acceleration down to zero, to the point of where it's just still in horizontal motion. See, it's kind of still barely spinning there, and the inertia kind of runs out, and it's all finished from there. So, that is Newton's third law for you. Hope you guys enjoyed. See you next time.